This brings us to what is arguably the most important mathematical question of our age. Are efficiently verifiable problems also efficiently solvable? So in 1971, way before NP-complete was a thing, Cook posed the question: is it the case that all of the problems in NP are also NP? Also in the set P, that is. And there's some intuition behind this. If an answer is efficiently verifiable, we can imagine doing some kind of enlightened guess and check, where we do some kind of educated guesses about where to go. And if each guess is really quick to check, then if we're sufficiently educated about our guesses, then we should be able to maybe converge to a solution. So what NP-complete did for us as a concept is it gave us like 5,000, 10,000 different avenues of attack about how we can try to be clever about our guesses. So with independent set, we can try and be clever in the context of graphs, and the actual verification procedure is trivial. We just have to figure out a way to kind of walk the landscape of all the different possible vertex colorings. It also gave us, for example, 3SAT. You can try and solve the problem in that domain. Again, testing a 3SAT it's trivial. You just plug in all the numbers and see what comes out. So as long as you have some kind of educated guessing and checking, maybe you could get to something. Now, even though that question was posed quite a long time ago, this is before I was born, nobody's found a satisfactory answer, either yes or no. Now, if it were true, if it were the case that efficient verification of a problem allowed you to somehow wander through the world of possible answers and get a solution quickly, then we basically say that P and NP are the same thing. That those problems which are efficiently verifiable are in fact solvable efficiently. And nobody knows the answer. So there's a poll. There's a guy who does a poll every while. I guess he's only done it twice. And he's asked famous theorists, what do you think? And so at the moment, in 2012, he said around 83% of people said no, 9% said I guess the answer is yes, and 9% said other, like for example, unanswerable or independent of the axioms we're trying to use. And so why is the opinion negative? Well, one of the most common answers is someone should have proved it by now. So Dick Karp, again, the guy in our own department who found those 21 important reductions, he said the only supporting arguments I can offer are the failure of all efforts to place specific NP-complete problems in P by constructing polynomial time algorithms. In other words, NP-complete unlocked thousands of avenues of attack, and we have all failed as a species to find anything. That's the best we know. Okay? Another argument, though, is simply that the creation of solutions to something seems philosophically more difficult than verification. The alternate argument has been that the ability to solve NP problems quickly would give us too much power, to a degree that seems unreasonable. Or in other words, that the creation of solutions to problems seems philosophically more difficult than verification. That is, I have some hard problem to solve. Think about how many times you've sat down with an old exam for 61B, and you try and solve it, you can't get it, but then you go and start working, you look at the solutions, and then you're like, oh, okay, I see, just do all these steps. It's easy to verify that the steps follow from each other generally. Well, it turns out that we can extend that to areas like just math proofs, right? So suppose that P equals NP. Well, it turns out that mathematical proofs are part of the class NP. Proofs are easy to verify, right? As long as you write all the steps out in a nice, unambiguous syntax that can be verified by a machine, that's quick to verify. And so once we have such a syntax and we have a P equals NP solver, recall that we're saying that if you can solve 3SAT or independent set, you can solve any NP problem, including, for example, math proofs, since they're in NP. And so this notion was first observed informally by Kurt Gödel himself. You might know him as a very famous mathematician who worked on some very fundamental mathematics. Maybe the incompleteness theorem is something you might have heard about if you're more mathematically inclined. So he had a statement which, translated into today's parlance, goes something like this. A linear or quadratic time procedure for what we now call NP-complete problems would have consequences of the greatest magnitude. So this is how we've changed things. For such a procedure, one that can do this, would clearly indicate that despite the unsolvability of the Entscheidungsproblem, the mental effort of the mathematician in the case of yes or no questions could be completely replaced by machines. So in other words, if you can come up with a math problem for which the answer is yes or no, well, a P equals NP solver, because it's math proof based, it's going to be able to find it. And so it is that we could say there are actually a bunch of problems out there that are unsolved. And 16 years ago, the Clay Mathematics Institute set up $1 million prizes for 7 problems they considered really important. The Hodge conjecture, the Poincaré conjecture, the Riemann hypothesis, and so forth. And the last one on this list is P equals NP. But what's interesting is, were this true, you could presumably maybe feed the solver a question, is the Hodge conjecture true? And it would spit out for you an answer, because an efficiently verifiable thing is also an efficiently solvable thing. And so you might be able to go home and get yourself $6 million, though you won't get the $1 million for the Poincaré conjecture. Someone already beat you to it. Now it goes even a little crazier than that. And here's where we're going to bring it back to compression. And this is somehow even this, it's very impressive, right? Okay, P equals NP, we can solve math proofs, but it's actually even crazier than that. So remember the Hugg plant. We have here a sequence of bits that can output the Hugg plant, right? Short sequence of bits, long sequence of bits, with really nice, beautiful visual structure. And so the question is, can we take a picture and run it through some kind of compression algorithm and get back a program? Because what's the best compression? Well, it's something that actually understands really deep semantics, not just repeated zeros and ones or whatever, but actually understanding rectangles and how this thing might have been built. Okay? So you might say to yourself, how would this help? Because it's not a yes or no question. There's no yes or no question here, but you can hack it, right? So an example of an NP problem that might be useful is there a program of less than 50,000 bits that generates hugplant.bmp in less than 100 million cycles? Now certainly, if the answer is yes, then it spits out a program, you run it for 100 million cycles, and verify it. And so if P equals NP is true, then that means that if the answer is yes, it gives you the answer, right there. So if P equals NP, you can actually solve this problem. So in other words, you can give a piece of data, whether it's speech, whether it's a picture like this, and just say, hey, I'm going to do basically, say the answer is no, then increase this to 100,000 bits, and then, keep going until you get the shortest program you can, kind of binary searching sizes and cycles, and you will eventually, using this automated NP problem solver, it can take any data and give you the most compact representation. So I'll close on this interesting quote from Scott Aaronson. He's a guy at MIT who thinks a lot about quantum computing, NP completeness, a theorist. He's a very interesting guy. We'll just close on this, which is, I've heard it said with a straight face that a proof of P equals NP would be important because it would let airlines schedule their flights better or shipping companies pack more boxes in their trucks. If P equals NP, then we could quickly find the smallest Boolean circuits that output, say, a table of historical stock market data, or the human genome, or the complete works of Shakespeare. It seems entirely conceivable that by analyzing these circuits we could make an easy fortune on Wall Street, or retrace evolution, or even generate Shakespeare's 38th play. For broadly speaking, that which we can compress, we can understand. Look at this, we're compressing, we have to actually understand the structure. It's written almost in English, right? And that which we can understand, we can predict. So if we could solve the general case, if knowing something was tantamount to knowing the shortest efficient description of it, then we would be almost like gods. Assuming P is not equal to NP is the belief that such power will be forever beyond our reach. Okay, that's it for today.